You get taken for granted after... All right, it's all right, it's all right. Thank you, Amit, for the lovely introduction. Okay, since this were... Yeah, that's good enough. No, I was born in Quebec, actually. It's a country next to Canada. Yeah. So we're closing down the lecturing part of this conference, so I thought it would be good to give a talk that's a little bit fun, so it's not too serious. There's going to be some mathematics, but not an enormous amount. There's mostly going to be a lot of pretty pictures. And let me start with showing you two pictures that are going to, once you've seen these two movies, you can leave, basically, because it illustrates everything that I want to say about the... There you go. So this is a mixing device containing some fluid. This is an actual simulation of a fluid dynamical flow. It's what's called Stokes flow that I discussed in my lecture earlier, so it's very viscous. So it's like honey. And the blue line is what's called a passive tracer, so it's just a kind of streak of dye that you squirt into the fluid. And then it's a peculiar mixing device. It's called a rod mixing device, where you only allow yourself to swap the rods, either clockwise or counterclockwise, but in this case, they're swapped clockwise. And you can see this is basically making Neapolitan ice cream or something, right? It's swirling the dye a little bit in there, but it's not doing much mixing in the sense that we learned during the lectures. So now let me show you almost exactly the same thing, but you'll spot the difference immediately. Right? So this is exactly the same. Well, it costs you exactly the same energy to do this than it did in the previous picture, but if you're interested in good mixing, this is far, far, far better. It creates it creates filamentation, as we saw in the lectures. There's an exponential growth rate here of the distance between the filaments. The distance between the filaments goes to 0 very rapidly, and so diffusion becomes important, and you would get good mixing. This is actually not such a bad mixing device. But there's some mechanical issues with it that I'll get back to later. So this is a specific examples of a much broader topic that I want to discuss, which is taffy pullers. So taffy, I called it candy in my talk. It used to be called candy. Now in the US it's called taffy. It's a kind of thing well, let me show you the movie and you'll understand better what taffy is if you're not familiar with it. There must be some Indian equivalent of taffy, I'm almost certain. So it's a kind of rubbery candy. So basically, now I can talk about it more, but I actually made it myself last summer as a kind of challenge to learn to make taffy so that I could talk about it and actually say what the hell is going on. So you boil some water with some sugar in it, and you have to boil it to exactly the right temperature to within a fraction of a degree. And if you don't get it right, it does something else entirely. It turns out candy making is extremely delicate. And candy making doesn't work well in a humid climate, so possibly that's a problem for the Indian candy making industry. You have to wait until it's very, very dry, which I guess some parts of India are quite dry. But then the problem is that when it comes out of your process, it's actually kind of brittle and kind of very hard. And you want to pull it to put air bubbles into it. And this used to be done by hand until the late 19th century. So there would be some gentleman would like hook up the taffy to a post and then would stretch it, then he would fold it in two, then he would stretch it again, and he would do this for hours. But around the late 1900s, taffy was becoming quite popular, especially on beachfront resorts in the US, and so people started inventing devices to do taffy pulling. So I'm going to tell you a lot about these devices, and I'm also going to tell you about the mathematics of this, because, for instance, a natural question to ask here is at what rate does this piece of taffy grow? In fact, if you're interested in mixing, this is actually quite important, because if instead you put a fluid around this, like in the first movie that I showed you, the rate of growth of the taffy is intimately related to the rate of creation of these small structures. So it's a measure of mixing in this sense. So in this talk, I won't really make a difference between taffy pullers and mixing devices, because in this topological sense, they work in the same way, and there's really no point in making a distinction. But most of this talk will be about taffy pullers themselves, just because I went on a kind of kick of studying the history of these things. So they're kind of hypnotic, right? So this is a movie by my former postdoc, Matt Finn. Sorry? Did I bring some? No, this is a kind of improvised, impromptu talk, right? So I didn't bring any taffy. And I could have made a batch and then brought it, but I did this last summer. I made a lot. It turns out if you make homemade candy, it is nowhere near as stable as store-bought candy. So like 3 or 4 days later, it becomes brittle and nasty. They must put all sorts of crazy crap into the commercial stuff so that it doesn't do that. It's true, right? Most of my chemical engineering colleagues, a lot of them work on stabilizers and things like that for food, right? Food likes to degrade if it's natural. You don't want that natural stuff. So the growth, I'm going to talk about the growth a lot. It also is, I often call it either the dilatation or topological entropy. That comes from the mathematical terminology. But it's basically the growth. The number by which you multiply the length at each time. So that number must be bigger than 1, basically. Otherwise, you're doing it wrong. There's another example. This is much more industrial. This is for making candy canes. So again, this is probably not a big tradition in India, but in the US, people love to give little candy canes at Christmas. And you need to make those, and you make massive amounts of those. And so they have mixing devices or pulling devices that work exactly like our taffy puller, except they're horizontal because, I guess, of the different way in which you want to do things. I'm not sure. I'm not sure exactly why this is horizontal, but it's a slightly different substance. But you make enormous amounts of this, as the title of the article implies, right? How to make 16,000 candy canes in one day. Here's another design. This is probably a more popular design for taffy pullers nowadays. This is the four-pronged taffy puller. So instead of having 3 prongs, it has 4 prongs, right, or the rods. I'll use the word rods and prongs interchangeably. This is the case where there are 4. And this looks more impressive, right, in the sense that probably if you're an inventor who invented this, it's actually a man called Thibodeau, so probably a former French-Canadian like myself. And Thibodeau probably thought he was doing it way better than the other people. It turns out if you do the mathematics of this, it has exactly the same growth rate as the 3-prong one. So it does nothing different, really. It just looks better. But that's half the battle, right? I mean, they put these things in store windows, and it's meant to attract customers. So, it's not completely ridiculous to make it more impressive. And this one has been studied more, actually, in the literature. So, for instance, Robert Mackay in the early 2000s wrote a whole paper on this, and then Halbert and Yurt really studied this particular system to death from the dynamical systems perspective. So let's go back to our original taffy puller, the one I showed you, the one that was not a taffy puller, the one that I showed you for mixing fluid in the very first movie. So in the very first movie, see, again, Michael mixed all the movies. Jesus Christ, this guy. Wow. So here's a piece of taffy hooked onto 2 rods, and as you switch the rods around, I'm going to decompose the motion of the taffy puller that I showed earlier. And so as I swap the first and second rod, you stretch the taffy this way, you stretch the taffy back, you stretch the taffy this way, you stretch the taffy back. God, these people who come in late, I told them yesterday, you miss all the movies. So there's these little symbols I'm writing here in the margins. It won't take much staring at this to realize what they're supposed to mean, right? Sigma 1 is the clockwise exchange of the first and second rod, and sigma 2 inverse is the counterclockwise exchange of the second and third rod. In mathematics, these are called generators of the braid group, and they will possibly pop up a bit later. In other words, the way we encode the motion of these rods is by looking at a space-time diagram of the motion of the rods if they were 2-dimensional disks, and you encode the information about the shape of this mixing device by writing down a mathematical braid. It turns out that that's the most economical way of writing it, and it captures uniquely what the mixing device is up to topological deformations, right? The whole point is that, the rods are moving around each other in a specific way, and it turns out that that is the same topological properties of a braid. And notice, by the way, that if you follow one rod, it goes here, then it goes there, then it goes there. So each rod does a figure 8. The figure 8 is a wonderful motion for these kind of stirring devices. Basically, if you stare at any of these long enough, the simple ones, something will be moving in some kind of figure 8. And in fact, you've maybe caught yourself doing this sometimes when you're mixing, when you're making a cake or something. You might spin for a while, but then you realize there's lots of, bits that you need to get to, so you start doing a bit more of a slicing motion, right? So the figure 8 is a very natural way of trying to stir things, especially when things are very viscous or polymeric. In fact, this has been long known in mathematics. This is a famous mural painted in Berkeley by the great Bill Thurston and Dennis Sullivan in the fall of '71. And written here is a so-called word for the shape of this curve. So this is a curve which is like my piece of taffy, has been stretched and folded several times. And so mathematicians have been studying this sort of thing for a long time, but not as long as people have been making taffy pullers. So Thurston died, unfortunately, just a couple of years ago, but he was one of the greats. And Fields medalist, who was responsible for the geometrization conjecture, which was proved by Perelman later on. This mural was painted over a few years ago. So there it is. That's the respect for history that people have. Okay, let me show you a MATLAB demo. Oops, I forgot to load up MATLAB. Hopefully. We have to wait until MATLAB starts. Sorry, my mistake. I totally forgot that I needed MATLAB for this. Come on. Let me tell you what I'm going to do. I'm going to run a MATLAB simulation that will kind of progressively add folds by moving the rods around. And we're going to count the folds. Maybe I should even just skip it. MATLAB is taking so long to start. And if you count the folds, and by the folds I mean this. Let's say you focus on one side. Oh, there it is. Let's say you focus on one side and you count how many folds you're seeing here. So see right now there's 5, right? And you can count how many folds you get by at each other iterations. It turns out that there's a technical reason why you would want to count how many you get at each other iterations. It turns out you see a sequence that you might recognize immediately, right? So this is what's the rule? It's the sum of numbers, right? It's the famous Fibonacci sequence, and it's just saying that the sum of the folds, the sum of the new folds is the previous folds, the previous 2 folds, right? So that actually immediately gives us the growth, because it means that the ratio of the number of folds converges to the golden ratio. In fact, there's a little bit of a trick. I'm counting here the folds on the left and then on the right and then on the left, because you're actually getting a kind of double Fibonacci sequence out of this device. So you actually get the golden ratio squared as the stretching. Okay, so for that reason we often call these golden taffy pullers, because the golden ratio is the most is the kind of the basic stretching mechanism, and it's actually the lowest you can get for a 3-rod taffy puller, meaning that's the simplest thing you can do, which is why I'm focusing on this device to begin with. Exactly. So we get that this multiplier, the growth that I was talking about for this basic taffy puller, is 2.618, right? The 1 plus the golden ratio, because the golden ratio satisfies this nice defining equality. Okay? So that's the golden mixer, or the golden stirring device, or the golden taffy puller. You probably know this, but I'm going to show you this construction just because I'll show you another construction which is different in a second. There's a famous construction of the golden ratio, which is where you take a rectangle, and the aspect ratio of the screen right now makes this not look like a square, but you take out a square, a unit square, and you demand that the remaining rectangle has the same proportions as the initial one, and that's exactly the definition of the golden ratio. That's exactly why the Greeks like this number so much, we are told. So again, I'm not going to do the MATLAB demo because it takes, I didn't set it up properly, so I'm not even sure where the codes are. So I'm just going to tell you, well, no, let me do it. Let me do it. You guys can wait a second, right? I thought they were here, but they're not here. So let me go to, this is super fun, right? Yes. There we go, not so bad. Okay, so this is my initial loop. Okay, and now I'm going to move the taffy puller in a slightly different way. So in the previous picture, I interchanged the first and second rod, and then I interchanged the second and third rod. Now I'm going to do it twice each. I'm going to change the first and second a full 360 degrees, and then I'm going to do the second one a full 360 degrees. So let's do one iterate. And that's what it looks like after I swap the first and second rod by 360 degrees. Then I have 2 folds, right? I have 2 folds living here and 1 here. And then I do it again. And it goes much faster now because I'm moving the rods really fast. So I have 2 here and I have 5 here. And now I'm going to switch the first 2 again, 360 degrees. And now my plotting already becomes a little bit dubious, right? I can maybe zoom in so we can still see it. And so we can see that there's still 5 folds here. And then you come here and you count, wow, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 folds on this side. Okay, so maybe we've got enough to write a sequence. I mean, I can keep going, but it gets dark blue very rapidly, as you might imagine, this is what happens with exponential growth. So we get a sequence like this. Remember I told you 2, 5, 12. If you kept going, you would get this. So now exercise to the viewer, what is the rule? Anybody want to guess? That's right. It's twice the previous one plus the penultimate one. So, 1 plus twice 2 is 5, 2 plus twice 5 is 12, etc. This actually generates a ratio that converges to 1 over root 2, 1 plus root 2. And actually that has a name. This is called the silver ratio. I'm going to bet that most of you have never heard of the silver ratio. Anybody heard of the silver ratio? Good. It is for some reason much less well known than the golden ratio. Here's a construction of the stretching is going to be 5.8. So the silver ratio is much larger than the golden ratio. In fact, by the way, notice that the silver ratio is 2.4, the golden ratio is 1.6. In general, you can define the bronze ratio, and then they're actually called I call them the metallic means. You can keep going, basically. And all of them fall between integers. That's why they're means, in a way. They're a way of taking a certain type of mean between 2 integers. So there's a generalization to the noble numbers, basically. And here's a construction. Take a rectangle, remove 2 squares, and demand that the final rectangle be proportional to the initial one. And that's the silver ratio. Okay? So for this reason, we call these types of missing devices silver mixers, or silver taffy pullers. Okay? And here's a surprise. Both of the major brands of taffy pullers, the 3-rod and the 4-rod one, have growth of the silver ratio squared. Both of them. They're identical. Okay? Now, it is not obvious why, in the sense that, remember that I can draw a picture of the very first one that I showed. It has a fixed rod, and then it has a moving rod like this, and then it has another moving rod like this. I think they're counter-rotating. And it turns out that it looks different from the figure, from what I just showed you, the one where you go twice one way and twice the other. But it turns out if you go in a co-rotating frame, if you rotate with the mixer, you can actually make it look like the other one. In other words, topologically, it's equivalent to the silver ratio one. Okay, and that's not entirely obvious, but it's something that you can do. You can convince yourself of in 5 minutes or so. Okay. So, I mean, the golden ratio and the silver ratio are special cases of what are called quadratic numbers, meaning you can write them in terms of square roots, as opposed to cubes or quartic roots. In that sense, they're always roots of second-degree polynomials. And this always happens with these kinds of devices. If I give you a device with an arbitrary number of rods, it can have higher and higher degree polynomial, giving it this rate of growth for the piece of taffy. There's a bound, actually, on how big the degree can be given the number of rods. So you don't know for sure, right? But there's at least an upper bound on the degree. And it's actually related to Teichmüller geometry, if you know anything about this. There's a dimension of Teichmüller space associated with certain surfaces that bounds these degrees. But I'll give you a very simple example here, because it turns out that for the 3-rod case, everything is much easier. And I'll show you the mathematics of how you actually compute these things when you have 3 rods. So for 3 rods, it turns out you should take a step back and go back to toral automorphisms, or maps on the torus. So the torus here I'm going to identify with the unit square with periodic boundary conditions. And a map on the torus is defined as a linear map on the torus is defined as a 2x2 matrix acting on some points on the torus, but then I take modulo 1 to keep everything on the torus. And it's well known that this matrix has to satisfy several properties. It has to be an element of SL2Z, meaning it has to have determinant 1. That's because the area of your initial torus has to be equal to the area of your final torus. and it has to be made up on only integers. That's because, well, there's several ways to see this. One of them is it has to be invertible. If it's going to be a homeomorphism, a proper map that can be inverted, then its inverse can't involve fractions, because then you would be mapping, you would be mapping, you would be double covering some spaces, it turns out, if they're not integers. Okay? So again, these matrices have to be 2 by 2, contain integers, and have determinant actually plus or minus 1, but we're going to keep determinant plus 1 for the purposes of this talk. That's whether you reverse orientation or not, right? Okay, so this is the most famous one. It's called Arnold's cat map. Maybe those of you who study dynamical systems have certainly seen this map. And the growth of a vector in this map is exactly given by the eigenvalues of the 2, 1, 1, 1 matrix, which is exactly the golden ratio squared. In other words, if I start two initial conditions on the torus and I hit them with this map, the rate at which they separate, which is the Lyapunov exponent for a dynamical system, is the log of phi squared. So it's exactly the same as my taffy polar, at least my first taffy polar that I showed you. So coincidence? Of course not, right? So there must be a relationship between these toral maps and the taffy polars. In fact, there's an exact relationship. That's what I'm going to show you now. So what's the connection? So here's the torus. You write, it's a donut, but I'm going to draw it as a unit square. And the little arrows means that edges are identified, right? Meaning periodicity. And so the cat map that I just showed you stretches, if I write a loop on the torus. So if I take, this is a loop, right? Because it starts from 0, 0 and goes to 1, 1. But 1, 1 is 0, 0. So this is actually a closed loop on the torus. It kind of goes diagonally on the torus. And if I hit that loop with the cat map, it stretches the loop very rapidly, right? Because it's basically a linear map on the plane, but I cut it back to make something periodic. And so it leads to very rapid growth it leads to filamentation, just like in my lectures on chaos and mixing. So the distance here, the distance between these lines decreases as 1 over the golden ratio squared. Okay? Now this is going to be our piece of taffy. This is basically the taffy, right? And the taffy polar is stretching it in some way. It's just not clear yet how this is related to the actual rod device. Okay? So it's going to be related to the loop, to the rod by using a certain kind of map that has a very, very scary name. It's called the hyperelliptic involution. But it's actually a rotation. So consider this map. If I take minus x, if I have the torus and I take minus x, it turns out I get a rotation by pi, right? Because if you think about it, I have my torus, I'm going to write the letter A, and if I take minus, A is a bad letter because it has a symmetry. No, B also has a symmetry. What letter has no symmetry, doesn't have left-right symmetry? Huh? B has up-down symmetry, so, okay. So then, minus x would map it to that, but then using periodicity, I can just glue my copy back there, and so, modulo 1, I've just rotated the r by 90 degree, by pi, right, by 180 degrees. Okay, so this map, iota, is an involution because its square is 1. That's the definition of an involution in mathematics. And then you can construct what's called a quotient space. What's a quotient space? The idea is you say, I'm going to take my torus, but I'm going to treat points that are related by this involution as the same point in my new space. So if 2 points can be mapped to each other on the rotation, then they are actually the same point. So again, if I draw a copy of my torus, and I arbitrarily decide to take the midplane as dividing 2 copies of my space, then this point would be identified with this point, because it is rotated into the point. And my new space now is only half the initial torus because I've kind of folded it in a funny way. So what kind of space do you get? This is the same picture that I just drew. So this is my torus, but now the arrows indicate 2 things. They indicate things that are identified because of periodicity, but also things that are identified because of the quotient with the involution. So in other words, this little portion is identified with this portion is identified to this one, and you see these arrows are identified because if I rotate by pi, this arrow maps to this arrow, etc. But then, of course, now I have 2 copies of the surface that I want. So the surface that I want is really this, right? It's really half of this. Because the other side is supposed to be exactly the same. Okay? So this is, again, a quotient space. And notice that there's 4 special points here. Those 4 points are fixed points of the involution. So they are the only 4 points that are identified to themselves under this map iota. Okay? So I claim that this new space is a sphere. So the original space was a torus. I claim that this is a sphere. Everybody believe me? I mean topologically, of course, right? Meaning up to deformation. So let's show that this is a sphere. It's a sphere, but with 4 punctures in it, and the punctures are the points P1, P2, P3, P4, P0, P1, P3. So let's show that it's a sphere. Here's my surface. What I want to do to show that it's a sphere is zip up these identifications, right? So these arrows correspond to things that are identified to each other, so I can glue them together, also called zipping. It's also called Pacmanization, because, you know, one way you identify this, you've got these 2 arrows and you kind of close them up, and it starts looking a little Pac-Man mouth when you glue these things together, right? So let me draw the picture. The intermediate picture would look something like this, right? You're folding these 2 arrows onto each other. So it looks a bit like the mouth of a Pac-Man, which is why I like to call this the process of Pacmanization, to close up the surface. So I close at the arrow and I zip, and I close at the double arrow and I zip, and I'm left with one outside arrow, so I glue that, but notice that once I zip that, I've really closed the entire surface. And it's got the bit of a shape of an American football, if any of you know what that is. Okay? And then an American football is basically a sphere, right? So I end up basically with a sphere, but there's 4 special points, and I've shown where my arrows correspond to with those special points. Okay. So what's the relationship with the taffy pullers? Well, those 4 special points are the rods of my taffy puller. But wait, you might say, there's only 3 rods in my taffy puller. Well, one of them is at infinity. Okay? There's a 4th rod which plays no real role, and it lives at infinity in some sense. That's normal in mathematics. Often there's something called the point at infinity. This is actually what's called the Riemann sphere. So P0 plays the role of a point at infinity. And the role of this point is just that you can't take the piece of taffy and unwrap it behind the device, right? So technically I could do this with the taffy puller, but there's the floor, you know, there's something keeping me from doing that, and that's the point at infinity if you want. Okay? And in fact, I can now use maps on the torus, like Arnold's cat map, and it will so-called descend nicely onto the sphere. And the reason I know this is because these 4 points are actually fixed points of this involution. So so you end up getting a map which commutes. The maps on the torus commute with this operation of taking a quotient. So everything is well defined. I can take the action on the torus and map it to some orbits on the sphere and come back up. Now again, the sphere is the sphere is basically the plane to me, right? Because I can take that 4th point and just unfold it, or think of an infinitely big sphere if you want, and keep your 3 rods here. But it's really an exact identification. Okay? So linear maps commute with this iota. So all those linear torus maps descend to taffy puller motions. So now I've actually completely characterized the space of taffy puller motions for 3 rods. They correspond to all possible linear maps of this form. Give me a linear map, and I will map it to some motion of 3 rods, which will give you which will stretch a piece of taffy, and the largest eigenvalue of the matrix will give you the rate at which you will stretch your piece of taffy. Okay, so it's a very nice and elegant construction. In fact, you can even make this a bit more constructive. Remember, I was always telling you about the elementary process of switching 2 adjacent rods. Well, it turns out that both of these elementary operations can also be written in terms of matrices. And so now the process of, so this one corresponds to switching the 1st and 2nd rod clockwise, and the second one corresponds to switching the 2nd and 3rd rod counterclockwise. The point P0, again, as I told you, is the point at infinity, so it plays no role other than preventing me from unwrapping everything. And so then I just can take products of these matrices to generate any possible taffy puller motions. Because actually it is known that these matrices generate the entire group SL2Z. So any element of SL2Z can be written as the product of these 2 matrices and their inverses. Okay, so there's some nice algebra that you can exploit here to be able to do this. Okay, questions so far? that is not a free group because it has relations. So that's a good question. So a free group is a group where there's no properties other than the group properties. But in this case, there's actually one relation, which is this. That turns out to be a true fact, which makes this not a free group. And this is actually called the braid relation and characterizes this particular group as the braid group on 3 strands, which is a special group in mathematics. People study braid groups very abstractly. They often don't even refer to the topology or the geometry. They're interesting groups in themselves, and they're closely related to another class of groups called quantum groups, which people also study, again, for various applications. So these are the generators for the braid group for 3 strings. Okay? Any other questions before I carry on? Before I tell you about the history, you might wonder what happens when I have more rods, right? So it turns out that you are then looking at the maps that you start from are maps on surfaces of higher genus. And then you still take this quotient map that I showed you. So you take, say, a torus with 2 handles, and then you take this hyperelliptic involution map, and you map it down to the motions of taffy pullers. So the same construction kind of works, but unlike the torus, we don't have a nice way of characterizing maps on genus 2 surfaces. It's not a linear space in that sense. Things are much, much harder when you have more rods. We do get lucky, though. Remember the 4-rod puller that I told you had exactly the same rate of expansion as the 3-rod puller? It turns out that the reason why that is because you can write the 4-rod puller as a motion involving all 4 of these points. Okay? So there's a special trick where now you have to invoke some other point as the point of infinity. But you take the motion of these 4 points. In other words, it's the same torus map that gives you the 3-rod and the 4-rod puller. You just make the identification of these 4 points differently. Okay? So it's surprising, but they really are the same object. So somehow the engineers discovered 2 ways of making the same mathematical object. They're very clever, these engineers. Any engineers here? You're very clever. Okay, now I'm going to tell you some history because that's kind of fun. So this past summer, I'm going to have to update this slide pretty soon because I guess it's getting into this summer now, but last summer, 2015, you know, I would always get an annoying person in my talks. I would say, when were taffy pullers first invented? And I would say, I don't know, I'm not a, you know. So I said, well, eventually you have to learn these things, right? Because you consider yourself, you're giving talks about this, so presumably you should know. So I figured I will learn where taffy pullers come from, and maybe there'll be something interesting. So I spent a month last summer looking at Google Patents, which is awesome. You know, we use Google Scholar for searching for papers all the time, but Google Patents is also a treasure trove of really interesting information. And I found probably 100 to 150 patents of taffy pullers. There's a lot of stuff out there. But here's the first one that I can identify as being the very first taffy puller. It's due to a chap called Virchow in 1893. So that's about the time I was talking about when, in the United States, these seaside beach resorts were kind of becoming very popular, and making taffy was one of the things that you bought on these beaches. Actually, it's something called saltwater taffy. I don't know if you ever heard of saltwater taffy, but it contains no salt water. It's just a name. Nobody knows why it's called saltwater taffy. I think maybe some places did start to put salt water afterwards, but I think the name already existed before they started putting salt water. So Virchow's device consists of a kind of 2 drums into each other, and the 2 drums have 2 pins. So inside of the drum, the 2 pins are moving like this. So you guys are now experts on taffy pulling, so you probably realize this is a terrible, terrible way of pulling taffy. Right? Because if I put a piece of taffy on here, it's going to just go like it's not even going to fold, nothing's going to happen. In fact, it is likely that this device was never built, which is true of many patents, and Virchow just used this then to sue everybody else. But it's not a very good idea. Okay? And he used this to sue people, which led to the great taffy patent wars of the early 20th century. Millions died. And And I'm serious, there was a really serious patent war, because it turns out there was lots of money in taffy pulling in those days, and people started inventing all sorts of devices. The first device that I can identify as being the real first taffy puller is this monstrosity by a guy called Dickinson, which filed it in 1901. And it's a kind of trough, right? And there's like two belts here, and there's a reciprocating mechanism. And there's a kind of chariot here with two pins and a fixed pin at the bottom, which is depicted here. And as the chariot moves around, when it gets to the end, it gets tripped. So the two rods exchange position, then it moves back, tripped again. So it exactly does the same as this motion. Topologically, it's identical to our original taffy puller, except it's a really, really awful way of achieving this motion. In fact, if you read the patent, I think you're actually supposed to slide these belts on and off to change the direction of motion. Like, there's no mechanism provided for the reciprocating motion. You're supposed to just take the belt and push it over, and then push it back, and push it over. It's just an awful, awful thing. But at least he's got the right idea, right? In the sense that this is now topologically interesting, and this would be a silver ratio kind of device. It's horizontal also, so it's more closely linked to the one I was showing you for making candy cane, but still, I consider it a taffy puller. And again, there's a big question as to whether this was ever built or whether it worked at all. This became a big issue in the later lawsuits. But Dickinson certainly seemed to think that this was a really great design. The first proper three-rod one was by Robinson and Dieter in 1908, and you can see they have the basic idea, right? They have the right idea of having a fixed pin and then two moving circular motions like this one. And we start seeing also something that I really appreciate, which is people start making very nice draftsman pictures of taffy pulling, which are quite useful for me because I used to draw these by hand, but now it turns out there's all these beautiful things in patents, which is not the place I would have expected to find these nice mathematical designs. So, you know, you can probably read off your silver ratio by looking at the folds here, if he drew his picture correctly, which I haven't double-checked, actually. Now enter Herbert L. Hildreth, the taffy magnate of Old Orchard, Maine. So he is probably the guy most responsible for the development of the taffy pulling industry, such as it is, because he owned the Hotel Velvet in Old Orchard, Maine, which burned down like 2 or 3 times, and he was sold, I guess online or something, is Hilbert's original and only velvet candy. Look where I had to look for this, you know. How many of you have looked at the Confectioner's Gazette? Thank God for Google. So taffy was very popular, and he sold it. He sold a lot of taffy. And then one of his employees cheated him. The perfidious Thibodeau invented what is now the four-pronged design, which we know and love, the one I showed you. He was the first one to really write it down, and filed in 1901, which is, by the way, almost the same as Dickinson, right? The first one that I showed you. So all this happened almost at the same time, which is why there were so many lawsuits. And Hildreth didn't like this, but eventually just, you know, bought the patent for $75,000, which is $2 million. So this is not a triviality, right? I've invented a new taffy puller now, and I don't think I can make $2 million off of it. So I think the industry is no longer as active as it once was. Okay, so that's the Thibodeau design, the first time we see a 4-rod design. And then, as I was saying, you know, the best ones have some pretty nice diagrams of taffy pulling. My personal favorite is Richard's 1905, which has really, really a beautiful picture of some taffy being stretched. This is the one that appears as the background of my original slide. But it's a different mechanism, right? It's a wheel with 2 pins, right? And then there's some arms coming in and out, and, you know, interacting with the 2 pins. But in fact, this ends up being exactly the same motion as the 4-prong, the 4-rod taffy puller, right? This is exactly the same thing as this one, you know, up to some minor effects. So a lot of these end up being very similar once you actually think about the topology of what's going on. The patent wars are interesting in themselves. I wasn't able to get to the bottom of it because I'm not a historian, but I did find something interesting. So many, many concurrent patents were filed in a few years. In fact, it went all the way to the US Supreme Court. And there's an opinion written by Chief Justice William Howard Taft, the same one who, I guess, was president before that, right? He was president before 1921, in the decision Hildreth v. Mastoris, 1921. And so, get ready to read this. This is brilliant. The machine shown in the Fairchild patent, this is the bad one, has 2 pins that pass each other twice during each revolution and move in concentric circles, but do not have the relative in and out motion or figure-8 movement of the Dickinson machine. With only 2 hooks, there could be no lapping of the candy because there was no 3rd pin to re-engage the candy while it was held between the 2 pins. The movement of the 2 pins in concentric circles might stretch it somewhat and stir it, but it would not pull it in the sense of the art. Wow, you know? They really understood everything. I mean, I think Taft probably had a very smart clerk. I don't think, you know, but this really gets to the bottom of it, right? They understood that the figure-8 motion was crucial, and you needed 3 pins for this to work, and the original device did not have 3 pins, and so they decided they did not invalidate the patents that came later on. It was not, you know, the thing about, you know, this is very much patent speak, right? The sense of the art, the term of art, and things like that. The criterion for a new patent is it has to be not obvious to somebody well-versed in the art that you're trying to do. So in other words, if it's considered obvious, if you make a modification to a device, but anybody who knows about such things would have been able to do it immediately, then you cannot get a patent. Of course, a judge has to decide that, so it's very subtle. But the point is that the Supreme Court decided that the 3rd rod was a non-trivial modification of the 2 rods. Yeah, so as I said, the Supreme Court really understood everything about mathematics, which I'm not sure is true today. Perhaps they do. Okay. So one question that I asked, though, is it possible to make a taffy puller that stretches at the rate of the golden ratio? It's not a coincidence. All the ones I showed you so far have the silver ratio as their expansion factor, because the golden ratio is actually quite tricky, right? Because if you follow a rod, as I said, a rod actually moves in a figure-8. As opposed to the other devices, because the rods return to the initial configuration, they can live on the same gear in some sense. Whereas for the golden ratio, you really need to have this figure-8 motion. So I'd always thought that you couldn't really do this. People did this in an experiment in the late 90s, and they moved the rods by hand, for instance. But of course, there are patents for everything. So eventually, I found one in 1918 by a chap called Nitz. And it's very clever. Look at this. It's 2 wheels, and there's 3 slits and 3 rods. And then there's something that trips the middle rod to alternate between the 2 cogs. So every time a rod comes there, it switches between the 2 cogs, and so it ends up doing a figure-8. So somebody invented a golden ratio stretching device in 1918, though I'm pretty sure they did not know that they were doing that. And I also wonder why. Like at this point, right, there were all these these taffy pulling devices, and they all work kind of similarly. I'm not sure why people were inventing more and more. I mean, this makes sense because it's still, the original patent was still not expired, so I guess they were just trying to do something different. But they're going to keep doing this for decades. So I don't quite understand what the impetus to make better and better taffy pullers is. Somebody needs to explain it to me. Yeah, well, but I mean, you know, there's a reason. Yeah, but you make new patents when you want to, first of all, it has to be either better or it has to be different from an existing patent so that you can do it separately, right? In this case, I don't really see what it does better, but it is different. But then later on, the patents have all expired, right? The original, it's 20 years for patents, right? So I don't really see why people were still designing taffy pullers. But they were, so, you know, I'm happy. Here's another one that gives the golden ratio, but in a different construction. So I told you that given these torus construction, you could often also use all 4 punctures in your taffy pullers. So there's this weird design by, again, the great Thibodeau, which uses 4 rods. So you have 3 moving rods on a wheel and an arm that goes back and forth for this kind of motion. And it turns out that this is a golden ratio device. Again, it's not obvious, but it's a great example. There's a well-known theorem by Franks and Ricken, which says that if your dilatation, if your expansion constant is a quadratic number, then somehow you have to be able to construct your thing from the torus. The torus has to be living under there, though it may be called what's called the branched cover of the torus. I'm not going to get into details, but it's kind of interesting that you can think of these devices as example some theorems, and these theorems, of course, came much, much later, right? So I'm trying to write an article about this right now to try to relate these different devices to different theorems, but it's taking a long time. Here's how this golden ratio device works. Again, beautiful pictures in the patents, right? But it's not too enlightening. I can just point out, though, that Thibodeau is really the king of the taffy pullers. He's got about 5 of these patents. So here, let me just show you some exotic designs at the end here. So people got weird later on. And so, well, this is the so-called planetary design. So when we talk about mixing devices, there's often designs that are called planetary. And that's where you have wheels within wheels, right? You might have a wheel. It's like Ptolemaic is a good way of putting it, right? You have a wheel, but on that wheel you have another wheel, and on that wheel you might have another wheel. And so you get what's called planetary motions, which are basically spirograph motions like this, right? So in this case, there's one rod that's moving around 3 rods. And I haven't yet computed what the expansion constant for this is. I'm working on it. And clearly you could run this device in two different modes. It's not clear to me which of these modes is better. This is actually a pretty serious one. This is called a mixograph, again because of its connection to this toy, the spirograph, if you've ever seen spirographs, right, which is for drawing. And I actually took these pictures at the Department of Food Science at the University of Wisconsin. So the mixograph is kind of fun. You've got all these pins. Let me show you a movie of the motion of the pins. So there's a lid, and the lid contains 2 gears with each 2 rods that are sticking down into this container. And then the container has 3 pins sticking out. And this makes a kind of complicated motion intertwine. And it's very well designed, right? The frequency was chosen that even though it's 4-3, right, the 4 rods make a 3-fold pattern, which exactly encircles the 3 fixed rods. So it's quite clever. And what you do in this device is you put a piece of dough, of bread dough, in it. And I thought that the goal of this was trying to stretch the piece of dough to make bread somehow. But it turns out that's not quite what they're doing. What they're doing is they're measuring the properties of bread. So they hook up, this is why it's called a mixograph. The graph comes from the fact that it's got a piece of paper sticking out of it like a seismograph. And as you pull the dough, it's measuring the torque on the arm. So it's telling you, and if you're a bread specialist, you can look at the curve and deduce the moisture and gluten content of the dough and all this stuff just from this experiment. And the reason why you don't want to change it is standardized, right? So in other words, there's one design for the mixograph and you don't want to touch it. So my idea at first was like, oh, I'm going to optimize this and make it much better. Turns out that's a bad idea. So here's the mixograph as a braid. I told you about braids earlier, and now these devices are getting complicated, right? So you've got 3 fixed pins and 4 moving pins. So if you do a space-time diagram, it looks like this mess. And you can map this, again, to study this, I mean, you have no handle on this, right? There's no way to study this simply. So you convert it to a braid. So basically what this braid is doing is it's recording the crossings at each point, whether a strand crosses in front of another or behind another. And so sigma 5, for instance, is the local crossing of the 5th strand over the 6th one, whereas sigma 6 inverse is the crossing of the 6th strand under the 7th one. Okay? And so you can visually read off the braid. And then there's actually an algorithm which was invented in the mid-90s by Bezvina and Handel. Mladen Bezvina is well, they're both famous surface dynamics people at Utah and at Northwestern. And, oh, actually, I'm not sure he's at Northwestern. But anyways, so you can prove that this thing is of the so-called pseudo-Anosov type. I mean, I'm not going to get into the mathematical details of this, but in this case, the expansion constant for this bread maker is the largest root of the an 8th degree polynomial. So it's no longer a quadratic number. It's no, these things are becoming more complicated. But I will point out one thing, by the way. This is a pretty small number, considering, right? So you would be better off running 2 periods of the simple 3-rod one than this, right? In the sense that I think there's, again, this idea that as you put more rods, things somehow get more stretchy. But exactly the opposite is happening here, right? This is by far the worst thing, considering by how much motion you have to do. So if the bread people were trying to somehow stretch their bread appropriately, I'm not sure they really succeeded, right? So, but you really have to know the mathematics to be able to predict this. Computing this polynomial is not easy. This is actually a very difficult calculation at this point. By the way, there's something special about this polynomial. Can you spot it? Sorry? All the coefficients are integers, that's certainly true, but it has a property. Try to read it from the left and then from the right. Try to read the coefficients from the... Huh? Yeah, there's some missing ones, that's true. I guess my question is too ill-defined, I'll just tell you. It's called palindromic, meaning if you read the coefficients in one direction, they read the same in the other direction. There's a reason for that. Can anybody guess as why that is? There's a kind of physics reason, surprisingly. That's right. So running the device backwards is like replacing x by x inverse. So you have to get the same expansion constant if you run the device backwards than if you run it forwards, basically, at least in these classes of devices. So you always get these kinds of reciprocal polynomials. A few years ago, I'm not keeping track of time very much. Oh yeah, time is there. Okay, plenty of time. A few years ago, me and my postdoc, Matt Finn, when we were still at Imperial, we did some optimization, and we created this class of devices that we called silver mixers, which basically we have a recipe now for building devices that have arbitrarily high expansion constant by adding more rods, and they do it in a kind of optimal way, meaning they go after the golden ratio. We proved in our papers that in some sense, in different senses, both the golden ratio and the silver ratio are optimal, depending on how you define optimality. But probably the silver ratio is the more relevant one. This first picture, by the way, is exactly equivalent to this, the three-rod puller. But then things get crazy. But it's not that complicated. If you follow one rod, it's always leapfrogging. It's always doing under, over, under, over. So the thing that Matt came up with was a way of providing gears to be able to always do this motion. But of course, I mean, you wouldn't want to build this, right? Or especially not this. An engineer would kind of laugh at you. But the 3 and the 2 are actually pretty reasonable devices to maybe try and build. I love this one, though. I think this is the most spectacular one. So if it's reasonable to try and build, then why not build it, right? So this is our Lego version of the device. This is the one with 4 pins, and it appeared on the cover of Science Review a few years ago, in 2011, I guess. It's starting to be many years ago. So Matt built this thing out of you can buy these technical Legos that have motors and things like that, right? So we bought the fancy Legos. I went to my grant manager and I said, hello, will I go to jail if I buy Legos on my government grant? And she said, is it for research? And I said, yes. And she said, fine. So I went and bought 400 pounds worth of Legos. It was super fun to be able to use a government grant to buy Legos. And so we built this device. Let me show you a movie of the device at work. So here it is. This is on my desk at Imperial, or on Matt's desk at Imperial, when I was at the time. So this was a long time ago, actually. And so the pins are moving around. This is Lyle's golden syrup, if you're English. Do they sell Lyle's golden syrup in India? Probably not, right? You have many local sources of sugar. So Lyle's golden syrup is a kind of treacly, kind of thick sugar syrup. And we're going to use that in the experiments in a second because it's very viscous. Now we're running it with water. And notice that, we're doing the right thing that experimentalists do. Is you don't visualize your experiment from the top. You put a mirror, a 45-degree mirror, and you visualize it from the bottom, right? Because it's much easier to, there's no gear on the bottom. So let me show you. This is the actual experiment running with a blob of dye. So it starts going, and Legos are moving in this kind of good fashion. And it seems to be mixing pretty well. Keep an eye on this arm. It's such a good mixer that it mixes itself. See? Just Legos everywhere. We thought about reshooting the movie, but we kind of liked it breaking apart. We're just running it too fast for the visualization, right? In the actual experiments, we ran it more slowly, but then it's less fun to watch. And this is actually a good lesson for Stokes flow. So remember, we talked about this viscous flow. On the left is a numerical simulation of Stokes flow, and on the right is the experiment. Look at how amazing this is. Fold, fold, little blip, little blip. Everything is perfect. So that just goes to show how easy it is to simulate Stokes flow, right? This is not like viscous flow is much better behaved than Navier-Stokes because the nonlinearities are not important. And so you can get extraordinary agreement with the experiments. But this is beyond extraordinary because it's not just the solution of the velocity field, but then the particle advection, the pushing of the material lines actually agrees, which is very surprising. So our paper on this optimization was in SciAm. If you're interested, I can give you a link. But at the same time, I talk a lot with Phil Boylan, who is really the person who introduced me to these ideas. He's a pure mathematician. And so we communicate a lot between each other while writing this, and he and his student, Jason Harrington, wrote a paper on optimizing what's called pi1 stirs, which is, pi1 refers to the so-called fundamental group of a surface, but I'm not going to go into that. Imagine that you have a bunch of pins, and you have one rod that you can move, and the only thing you're allowed to do is move that one rod around the other fixed pins. Then what is the optimal way of stirring? Right? What is the best taffy puller that has only one move rod? So those are what's called pi1 stirrers, because you can map the generators of this motion to the generators of the fundamental group. But I'm not going to get into that. So here's a few more taffy pullers, just to finish off. So this is, I like this one a lot because it's very simple, and it has a very exotic kind of design. It's because it's got 5 pins, 3 fixed pins, and I guess you're just supposed to stand there and rotate the thing. This guy did not spend, he probably spent more energy drawing this picture than on building his apparatus, right? I mean, this is not very impressive compared to the other patents that we saw. But I've never seen this built. Maybe I'll build it for fun. This one is also pretty cool. This is like an arm that moves up and down, but at the same time it kind of shifts. So you're kind of, like the taffy comes down on one side and back up the other. So it's really doing like an infinite chain of these sigma 1, sigma 2 inverse type exchanges. So that's actually a pretty good design because it scales. I could put more and more rods here and it would do better and better. It'd probably become harder to build, but still, I like this design a lot actually, 1914. Here's one of the wackiest I've seen. So like, there's a rotating arm with 2 pins off center, there's 2 fixed pins, and then there's an oscillating arm just for good measure, right? Again, I really doubt this thing was ever constructed. But it would be spectacular to watch it stretch taffy if it had been constructed. Maybe I should. If anybody feels like building that, I would really love to see it. Okay, so here's my own attempt at doing this. With an undergraduate student at Wisconsin, we built this device. Our thinking was, well, we have computers now, we can simulate these devices before building them. So let's see if we can take one of the existing devices and modify it just a bit. So what we came up with was to take the 4-pronged device, right? Remember the one that has 4 2x2 wheels, but to modify it in a very trivial way. We shifted the arms a little bit, but then we also extended the axis of rotation to be a pin. See, in the design of the 4-pronged puller, the arms from the side look like this, right? There's a pin and then another pin. But there's no, you can do this. You can extend the axis of rotation so that it catches on the taffy itself. People don't tend to do this, I think, because the thinking was that pins that don't move don't do much. But this is not true. Pins that don't move are in the way, and they may cause a lot of growth. And so that's what we did. The gray ones are the extension of the pins, and then we built it in my basement. And it's got an enormous expansion constant. It's 14. Every period of this thing, you multiply the length of the taffy by 14, compared to 6 for these standard devices. Okay? Again, these are multipliers. So the difference between multiplying by 6 and the difference between multiplying by 14 is pretty dramatic. So then we tried making taffy, and this is my first attempt. It was all this droopy mess. But eventually I got better at it. Maybe I can show you the action of my device. So here it is. So now, this is just to see the rods moving. And there's an engine powering it, and it turns out I have to disconnect the engine when actually doing the thing, because the engine wasn't powerful enough to pull the taffy. So, okay, we're not great at this, right? I mean, and at first it looks like a mess, but it'll smooth out in a bit. It'll get better, because it's so fast at stretching anyways, right? It basically creates like 4 plies and folds them onto each other. So it's pretty effective. I don't know if it's worth so I went to see the patent office at Wisconsin and told them about this. And I wouldn't say that he laughed at me, but yeah, he didn't really think there was commercial potential for taffy pulling devices these days. But, I still think it's interesting. There are lessons to be learned here. I mean, it's not all facetious. Because some of these devices are so useful for actual stirring of viscous substances. And the stirring of very viscous and polymeric substances is perhaps more important than you might think, especially because of the pharmaceutical industry. So imagine that I'm making multivitamins, and I throw everything in a bucket, and I have to stir that bucket. What will happen if you get a multivitamin that has nothing but one type, nothing but iron or something like that, right? That would be bad for you. So it has to be mixed perfectly. And these are difficult things to mix. They can be very pasty, very polymeric, right? So designing mixing devices that do precise mixing by a clever motion of rods is important. And it's not the same as turbulent mixing. In turbulent mixing, right, combustion and things like that, the way you mix is usually by whacking the thing as hard as you can, and then it mixes, like your coffee cup, right? There's no subtlety involved. But when you make a cake, of course, there is some subtlety involved, right? So low Reynolds number mixing, so viscous and polymeric mixing, actually requires a delicate motion. And very often, actually, it has to be delicate because the polymers might be fragile. So you don't want to stretch them too fast, otherwise they break. So there's lots of constraints. There's a lot of relationships to combinatorics in this, it turns out. And mixing, especially at these low Reynolds number, is a little bit like shuffling cards. It's about creating entropy. And these designs, later on, some of these taffy puller designs were actually taken up in specific types of chemical mixers. And really, all these topological dynamics methods that I mentioned really date back to earlier than Thurston, but Thurston's really the man who developed this stuff and made it what it is today. And people are still doing research on this field. I'm not going to go over that. Pseudo-Anazov maps are still very well studied, which are these maps corresponding to these motions of pullers. And here's some references. Thank you so much. Yes? Yeah. Okay. So the question is whether the rate of mixing is going to be uniform. Absolutely. Stretching or mixing, it doesn't matter. So what I've done today is topology. So I said nothing about what happens in the space in some sense. And you're perfectly right. If you're optimizing these things, right, if you're optimizing in a fluid, then you really need to be careful because the stretching could be different in different areas. So this is not a very good measure of mixing for fluid dynamics. But for taffy pulling, it really is. So you're asking if the rate is uniform, and it is. It's kind of surprising because it looks like it should be non-uniform, right? But you have to think that each piece of taffy, even though it might get stretched less on one leg, it'll eventually go to the other leg. And the rate of stretching is an average over all the different pieces of the stretching device. So in fact, at the end, each piece of the taffy puller gets stretched at the same rate. Each piece of the taffy gets stretched at the same rate. There's no stagnation point. That's what this Pseudo-Anazov condition gives us. There's more maps than Pseudo-Anazov maps, but this Pseudo-Anazov property is exactly that the motion of the rods is, in a sense, irreducible, meaning any piece of taffy that you put there will propagate to the entire thing. Okay, it's a kind of Markov property, irreducible Markov process properties that you can define for these things. I don't know that many have been filed in the last few years. I don't know when the last taffy patent puller was filed. That's a good question. I'll have to look at my notes to see what the last one was. It may still be going on today, for all I know, right? I mean, exactly. That's right. The real action. That's something I would like to do eventually, is to also review the literature of chemical mixers and things like that. But I mean, eventually I have to realize that I'm not a historian, I suppose, or either decide that I'm a historian. I don't know. But the thing is also explodes, right? There's 100 patents on taffy pulling, but there's possibly hundreds of thousands of patents on chemical mixing devices. So it's not going to be that fun. Question in the back? Yeah. That's a good question. So everything here was planar. And the reason is also my focus. For taffy pullers, everything I know that exists is planar. For mixing devices, of course, there are 3D mixers, right? There are things that exploit three-dimensionality for various reasons. And those are very interesting, except that they don't fall under this theory at all, right? So they're fascinating, but there are serious mathematical obstacles to doing the same kind of thing that we did here for the three-dimensional case. For instance, the classification of all possible maps, a homeomorphism of a three-dimensional space to itself, this doesn't exist, whereas there is such a classification for two-dimensional spaces. So it would be great to be able to do this in 3D, but at this point, I seriously doubt whether it can be done to the same level of mathematical elegance or compactness. Yeah.
Mixing is different from turbulent mixing.
Yeah.
So how the rate of mixing differs in static mixing?
Well, so taffy pulling, of course, is not really a mixing. So you mean in fluid dynamics, of course, there's going to be a fluid, right? So what happens if you try to use one of these motions to stir a fluid, it will work, but the mixing will not come from the topology. It'll come from the fact that when you move a rod, it sheds eddies, right? So most of the mixing in turbulence occurs because of the eddies. The rods that you put in there, your spoon, right? It's not the spoon that's actually doing the mixing. It's the eddies that are shed by the spoon. But at low Reynolds number, there are no eddies. So it's really a question of vortices. There's no vortices in these situations. Yeah. Thank you.